Alright guys, so I am going to be going through the packet just like I would on a normal day in front of the smartboard for you guys, but obviously you guys will be following along on the computer. So I want you to be writing down as I speak. Make sure you get all these notes so when we come back on Thursday we can pick up where we left off, okay? We are starting our last and final unit of the semester, so woohoo! Almost there, guys. This unit will be broken up into two parts, so a solving and a graphing piece, kind of like the one we had last unit, but before you groan, this one is a little bit easier, and I think you guys will find this one pretty straightforward. You won't have to memorize as much as you did for the last unit. I think you will overall like this one a lot. So what this unit is called is our Unit 5, and we are starting with our log and exponential functions. So these log and exponential functions are inverses of each other, so they need each other to undo, and eventually we'll be solving, so that will really make a lot more sense. We're going to start out with a task, and then you guys are going to be going into rewriting, so going from log form to exponential and exponential to log. It's going to seem difficult at first, just like everything you learn for the first time, but I think you're going to find it a lot easier. So let's go ahead and get started. Go ahead and flip to the next page. So we are starting with a little warm-up activity. So in this activity it says bacteria count in a heated swimming pool is 1,500 bacteria per cubic centimeter on Monday morning at 8 a.m. and the count doubles each day thereafter. So each day that count of bacteria doubles. Gross, but we're going to go with it. So on Monday, obviously we start out with our 1,500, and if we double that, we are going to get 3,000. We double that, we get 6,000. We double that, we're going to get 12,000. Double that, 24. And on day 5 we will end up with 48,000 bacteria. Now bear with me, this pen that I have is a little wonky, so I'm trying to get used to it. So now if we look at number 2, it wants us to kind of estimate the number of bacteria we think will appear at 3.25 days. Now we don't know for sure, we don't have a function that we can plug it in to figure that out, but 3.25 is obviously going to be between 3 and 4. A little bit closer to 3 than to 4, so if I'm just going to throw some numbers out there and see kind of a guesstimate. So I don't know, we could say 14,000 would be a good guess. 16,000. I don't know, 17,000. Something around there. So let's go ahead and hold those thoughts and see if we can figure out how to actually plug that in. If we can create an equation from this information that we're given about the bacteria. So now, moving down, we need to go ahead and point out what are going to be our x and our y values, or our inputs and outputs of the function. Now your x values are always your inputs, or your independent variables, and y values are your outputs, or the dependent variables. Looking at the table, really, if you guys think of it up here, x is going to be our time of days, and y is going to be our number of bacteria per cubic centimeter. So the amount of bacteria depends on how many days have occurred throughout the day. So x would be our time, and if we want to get specific, time in days. And then y would obviously be what we get out, or our number of bacteria. So not too bad. Pretty straightforward. We're just trying to figure out, as the days move on, how much bacteria is in this nasty pool. Okay? So go ahead and flip to the next page. Here they've kind of set up a table for us. So we are seeing what happens each day as we start out with our 1,500 bacteria. So we know it doubles. So obviously 1500 times 2 gave us our next count, which was 3000. Then we did the 3000, which is the 1500 times 2, and we multiplied it again by 2 to get me my 6000. And then we said 12,000, 24,000, and finally at day 8 we had 48,000. So looking at the pattern, because you know in math we love our patterns. I'm going to go and move this down. You always start out with your 1500 bacteria count, okay? And each time it built on itself. So the number before was always multiplied by 2. So if we look at the first one, we did 1500 times 2. Then we did 1500 times 2 times 2 and got that 6,000. So I guess you guys can probably figure it out at this point, but for this one I'm going to do 1500 times 2 times 2 times 2, or multiply 3 times. Sorry guys, this pen is making it really hard for me to write. I'm doing my best here. And so the next day, on day 4, we're now going to be multiplying by 2 times 2 times 2 times 2. Whew, that's bad, but you guys know what I mean. And then last time we would multiply by 4, we would now multiply, since we're at day 5, probably by 5 2's. Now you can check yourself, but in your calculator you should be able to multiply 1500 by 2 times 2 times 2 times 2 times 2 and get your 48,000. Okay? So let's go ahead and start looking at the pattern. Another more, or an easier way to write 2 times 2 times 2 times 2 times 2 would be to raise it to an exponent. And ooh, there's your key word, because we're talking about exponential functions. So really, this is the same thing as saying 1500 times 2 to the 5th power, 2 to the 4th power, 2 to the, ooh, that's so ugly, I'm sorry, 2 to the 2nd, and 2 to the 1st, so on. So if we think about it, our initial value and the thing that stays the same, keyword, in the expression for the number of bacteria is always what we started out with, our 1500. And then we always doubled, but what is changing is actually the exponent of 2. So what we rose 2 to a power of, right? Or how many times we multiplied the 1500 by 2 to get our next number, or doubling the number before the next. So for this times, we could say the number of times we number of times we multiplied by 2, okay? So let's go down. Let's try to see if we can think of a pattern. So we're obviously talking about a function. So instead of saying y, we're going to use our beautiful function notation that we know means the same thing. So we always have y equals, or in our case, f of x equals. We know we have to start out with 1500, and every time it is being multiplied by 2 times a value we are not sure of unless we know the day. So something that is unknown, or that we plug numbers in, because obviously 2 was being raised to a different power depending on the day, we can call that x. Alright, so this is our first real look at what an exponential function, how it reacts, what it looks like. So now we can figure out how much bacteria is in the pool after 3.25 days. We already said on the previous page that days, or time, is our x value, and we get out our y value, which is our number of bacteria. So to figure that out, we should get 1500 times 2 to the 3 point, oh my gosh, let me, hold on, I can't even, that's so ugly. I I gotta get another pen. Hold on. Let's try this pen. Maybe I can do a little bit. 2 to the 3.25. It's a little bit better. We're going with it. So, in your calculator, go ahead and put that in. Don't worry, I'll wait. Okay, so you probably laughed at me and you didn't even actually put it in, but if you did put it in your calculator like a good little student, you should have got about 14,270, which is close to the kind of guesstimates I threw out there to begin with, okay? And when we're talking about 14,270, we're not talking about days, but bacteria, okay? So, I was pretty close. Pretty proud of myself. But I cheated because I've also already done this before, so I knew the answer. Now, you can go ahead and graph the function that we found in part 4, so right here, in your y equals, and go ahead and trace it to get to when x is 3.25 days, but really plugging into the equation was a lot easier and a lot quicker. Okay, so now, in number 7, we're going to move past number 6. Go ahead and graph it. You can pause the video, graph it, check it graphically if you would like, or let's move on. So now it's saying if nothing is done and the bacteria continues to double, so we have the same pattern, how long will it take for the count to reach 3 million bacteria? Gross. But it wants to know how long will it take to get that disgusting. So write an equation to represent this situation. Find at least 2 different ways to solve the equation. Ooh, okay, so now, let's think. I know I'm not plugging in 3 million in for x, because if you guys remember from this part, x is your time. So really, I'm setting my 3 million equal to my equation that I came up with, times 2 to the x, and I need to solve for x because that is my number of days, okay? So, we don't really know how to do that yet. This is the whole purpose of this unit. And this is going to be kind of the first unit you guys get to, and you will see that you have realistic, I don't know, applications that you have for the real life, especially when we get to the end of this unit. There will be things from this unit that you can relate to your day-to-day life, like paying your student loans off if you go to college, you buy a house one day, calculating your interest rate and how much time it's going to take you to pay off a loan at some kind of interest. So it is interesting. I know it's still math, but it is helpful, okay? So we're going to come back to this. We don't really know how to solve number 7 yet. So in order to solve for x, we've got to know what it means to be a log, how to undo it, rewrite, all these things, so I can get to a position where I can solve for x, because I don't really know how to solve for x when it is in the exponent, okay? So this brings me down here to what is a logarithm. So if you guys look through here, they have gone ahead and rewritten our formula for us. So we were trying to find that 3 million bacteria. So we need to use a function called a logarithm. This one, our equation we started out, was an exponential function, so we had to raise to an exponent. And I told you guys at the beginning, log and exponentials are inverses of each other. So, in order to solve for that, they put t, if you guys see where I underlined, they put t instead of x. Same thing, they just wanted to be fancy and represent time with a t instead of an x like we normally would do. So, what is our independent and dependent variable? What does it represent? We already kind of talked about this, but again, x, or our independent variable, is our time, and y, or our dependent variable, depending on the time, we get out a number of bacteria, okay? I'm just going to put back. You guys know what I mean. Now, if anything out of this whole unit, this is what we will be focusing on and learning the most, okay? I want you to start, know it. We are going to be testing ourselves